Hey guys, how's it going? My name's Andrew, and I'm a somewhat of a crypto veteran. I've been around, I got my first Bitcoin in 2014. And what I'm seeing right now in this next bull run here is that there's a lot of new people coming into the space who've heard about crypto and like, what is this thing? And also, a lot of new people are coming into NFTs right off the bat. And my guess is that a lot of these people might not know like what makes an NFT like actually different than when you send a JPEG from one place to another, right? Like what is the difference between a when you send someone a Facebook message photo and obviously, they understand how they can use the blockchain, but maybe they don't really understand how it's actually functioning. And so that's what I'm going to be talking about here is what is the real value proposition of the blockchain? What is all of this new stuff that we're coming out with? What is it actually attaching to? What's the foundation that everything rests upon? So I'm going to be answering those questions and also explaining the basic building blocks in a very, very basic way. So this is not a computer science course, but we're going to be talking about some of the most important parts that you need to understand to see the magic and the beauty that Bitcoin actually gave us when it first came out back in the olden days. So anyway, so buckle in, strap in, and let's go through this. It's not that long. It's 11 slides. So hopefully we can bang this out pretty quick. All right, so first thing is, let's start off with a nice bold statement, why don't we? Crypto is a technology that will change our lives more than flight, computers, or the internet. Do I believe that? Absolutely. I wouldn't have wrote it otherwise. So if you look at this, this beginning of the flight, back then, probably people doubted, oh, is this even really going to work? I was tempted to say, is this going to take off? Because, that would just be a really bad pun, but I love my puns. Anyways, then computers. Think of how many people would have had no idea where the computer would have went, right? All the things that we've done with the computer since then. I really believe that's where we are with Bitcoin and with crypto in general, is that we're maybe just slightly past this version now because it's not the very beginning, but people still don't take it as seriously as it needs to be taken because this is a game changer. So anyways, moving on. I'm sure you wouldn't be watching this if you didn't have some interest. So let's take a look at this. So the very beginning of Bitcoin, crypto first began when an anonymous user by the name of Satoshi Nakamoto published the Bitcoin white paper on Halloween, October 31st, 2008. And what was going on during that time? Well, if you guys remember, which I'm sure a lot of you do, there's a massive global financial collapse happening. And a lot of people postulate that Bitcoin was actually made and put out as a response because built into the blockchain, there's a post about the financial collapse. You can look into it if you're more curious. But later on, Bitcoin actually went live on January 3rd, 2009. And what it did wasn't actually really new as far as the small components that made it up. It was the way that they were put together. So Bitcoin's invention was a lot like you take bread, meat, cheese, and you make a sandwich out of it. And that was the beauty of Bitcoin, to me at least, is that the way these different parts were arranged, that's what really made it stand out. So let's dive into those parts. And this isn't a computer science course, as I said. This is just like a bare bones explanation of what the things you need to know. And those things are here, the parts. So before we can understand what a blockchain is, you need to understand a few things. So first thing is we have something called an array, something called a hash, and something called a linked list. And don't worry, this picture here was actually just it was put here to look confusing because actually it's not that confusing. I just wanted to basically show you guys, it's like, this might look super confusing, but it's actually pretty straightforward if you just look at it from the high level of what's going on. So let's dive in. So an array is simply a predefined area for data to live, sort of like a parking lot. So it's of a set size and it can only hold a certain amount of cars. So if you look over here, how it has this bracket 0, bracket 1, bracket 2, bracket 3, bracket 4, you can think of these as like the number of the parking stall. And then the number here, 73, is like the data that lives in that number parking stall. So this might be, I don't know, like a Corvette, and this could be a minivan, and this could be an SUV, and that could be a truck. So they're going to park different vehicles in all of these different parking stalls. But parking lots don't usually just spontaneously grow or shrink in size, like to just meet the demand of the cars. That'd be nice if it did. But instead, they build a parking lot, and then it's just statically that. So they might build it for like 30 cars or 50 cars or 100 cars, and that's it. It's not going to change unless they do more construction. So that's what an array is that you predefine the size of it, and then cars can come and go, and you can park data in there, and then it can leave, and you can put another thing in there as well. And that's what an array is. So why that's important is because each block in a blockchain is an array of some set size, which is called block size, meaning there's an array inside a blockchain, and it's a certain size. So Bitcoin has a block size of 1 megabyte, for example. And that doesn't have to stay the same. Different blockchains can have different parameters, but that's just the way Bitcoin's set up. Okay, so moving on, the next thing we have to learn is what's called a hash. So I live in Canada, so I use this. I actually put this together for a presentation, and I'm just basically reusing it because I think people might find this helpful. So anyways, so a hash is a machine built from code that takes an input like Canada and outputs the string. So it's going to take the input Canada, put it in, and then it'll output this number. So the number that this is outputting is actually the real number that would come out from what's called a SHA-256 hash, and that's the type of hash that Bitcoin uses. So this data becomes this. And then you'd be thinking, well, wait a minute, why would I want to turn this small little word into this really, really big long number? That doesn't make any sense. I'd much rather just use this small word. Okay, but think of it this way. This number, once you find out that this number never changes in size, even if this number or this input grows or shrinks, we could take like 100,000 books. Okay, the biggest books you can think. They could be Bibles, they could be whatever. You could take 100,000 of them with all of their pages, all of their text, every single sentence and period and space and character. You can put it in here and you'll still get the exact same length. So that is the power of a hash, is that it's the same size irregardless of the input that goes into it. And if that wasn't enough, the true power of the hash, I think, is that you can reverse it back by inputting the hash and then getting back the input. So in this case, Canada. So you could re-put this back in, and then you can go backwards to get what your input was. So you don't just get some random number, you can also find out what that data was as well if you go backwards. So that is really, the hash in general, is it's basically you take an input, it gives you an output, and then you can use that to get back your output. So it's a way of compressing data. And also the most beautiful part is let's say there's those 100,000 books and I just went into, the 213th book, and I just went on to one of the pages and I just hit backspace on one character. I just removed a period or something. This entire number would then flip and change. It would be a completely different number. Meaning if I compared the two hashes, I would clearly be able to tell they're not anything alike. There's something different about it. So what this does is it lets me know that this data at a glance has not been changed. It's always the same. And so we've been using hashes and we've been using arrays for many, many decades. They're not new whatsoever, but they're going to be put together with blockchain in a really cool way. Okay, so moving on, our last thing we have to look at is called a linked list. So a linked list is another type of data set in computer science. And this one is actually showing a doubly linked list. There's either singly linked or just linked lists. And then doubly, don't worry about it. It doesn't really matter. We're not doing computer science, so it doesn't matter. We don't have to specify. The basic is with a doubly linked list, you can go back and forth, versus the other one is just one way. So it's like, think of a one-way street or a two-way street. That's basically what a doubly linked list is. Anyways, okay, so linked lists are ways to create infinitely expandable data sets. They're sort of like creating a shortcut to a file, and then it points to where that file exists. Another way to think of it, if we use the parking lot analogy, is like you could drive your car into like a teleporting pad, and then it'll teleport you to the next parking lot if you, let's say the first one you got to is full, and you're like, oh no. So you got to the end of it, and then there's just a teleporter pad, and it teleports you to the next parking lot. And then you're like, oh, this one's full. So you go to the next teleporter. And then you're like, oh, I can go on this one. So basically, it's a way of creating like a chain of parking lots, but they don't have to be parking lots. Like they could be whatever you want. So this is why it's called a payload. So you can have your payload, and then you have a pointer that goes back or forward. And so the way I like to think of this is a book. So the payload is an array in our case. So it's like a piece of paper. So if the piece of paper is a set size, we know if we use a static size of a font, so let's say we go with like a 20-point font, then we know that we can realistically only fit so many characters inside that page before what? It fills up. So what do? Well, we can flip the page in the book, and then flipping the page is basically what a linked list does when it goes next. Then we get to our next page, we can fill that up with more data, or we could go backwards and go back to the previous page. So that's all a doubly linked list really is it's basically like a book with multiple pages where you can flip back and forth. And they're all bound together and chained together by basically the book binding. So yeah. Okay, so that's basically it. We have the basic building blocks of what we need. So now let's put it all together. So I'm going to credit the person who put this together because this is an amazing site. I'm going to put that in the video description because this is just phenomenal. This is what really helped me. There's an example. I didn't put this part together. I just took a screenshot after I played around with it, but there's a website where you can actually play around with this yourself. And if you try it out, it's amazing. So props to the guy. I'm going to put both his video link and his website in the video description. So please go check it out. Okay. So anyways, so this is what a blockchain looks like. So we have a block number, 1, 2, 3, 4, 5, 6, and so on. We have this thing called a nonce, which we'll get back to in a second. And then here, this is the special part. This is our array. So the array or the data is where we can write Bob pays 0.2 Bitcoin to Alice. So these are transactions. And so this wouldn't actually look like this. Like instead of Bob, we'll actually have an address number and then pays, it'll send to another address. So it'll actually look a little different, but it doesn't really matter. It's doing the same thing. So it's basically just recording one transaction or one amount going to another. And when we fill this thing up and we get to the bottom, then guess what? The block is filled up. So what we do is we have to hash it. So this is where the magic starts to happen. So what happens first is we take all of this upper information here and we put it through a SHA-256 hash. And then what happens is we get a hash output. And so the Bitcoin software is looking for, or blockchain software in general, is looking for leading zeros. So in this case, it's hard to find a hash that starts with a 0, and it's even harder to find 2 zeros, and even harder to find 3 zeros, and so on and so on. So the Bitcoin software can basically say, we want a hash. A hash is only valid if it starts with 4 zeros. So what you have to do is you have to kind of play a guessing game. We're not going to change this because this is our transactions that we're going to submit. So instead, we cycle this thing called the nonce. So it starts at 0. Does that work? No. What about 2? No. What about 3? No. What about 4? No. So eventually, after you keep trying these, you'll get to 57,763, and that was the first nonce that would actually give you 4 leading zeros. And so that is what the Bitcoin, like when you go to mine something, if you click mine, it's literally just going to try all of these different numbers until it finds the right number, and then it's going to say, I found a hash with 4 leading zeros. Let's submit it to the blockchain. So once that goes through and it gets accepted, then the next block starts. And so here's where things get even more interesting. So notice that we're going to include the previous block right here. So we have the same number, which is 4 zeros, and then it says 61D over here, same thing, 4 zeros, 61D. So this one is linking back to here. Remember that linked list we were talking about? So that is how we chain the blocks together, is through the doubly linked list. So the previous is this is the previous hash from the previous block, and so that's how you can find where that block is. And don't worry if you don't understand exactly how that works. Just think that's how, so we're including this, and it has to stay here. Okay, so anyways, so we're into block number 2. We put our new transactions, we fill it up, then Again, we do the nonce, we mine it, and then boom, we found our new hash. Okay, great. Do the same thing again, same thing again. Okay, so that is basically how the block is building upon building. And in Bitcoin, the block time is 10 minutes. So you're going to have a new block every 10 minutes. Different blockchains have different block times. Some are really, really fast, and they're like 500 milliseconds for every block, so 2 blocks a second. But they do have trade-offs, and we're not going to dive into that because that's just outside the scope. Doesn't really matter. I'm just wanting to bring up the fact that not all blockchains have the exact same parameters. They have different ones. So they're sort of competing to be, the best and so on. So anyways, okay. So what's the big deal? So what else can we learn from this? Okay, well, this is where the real magic sauce is. Until we get to this point, nothing really was that super cool. What if, let's say I want to do something fraudulent. Like let's say there's an attacker. So let's say they wanted to, instead of Ron pays 1.2 Bitcoin to Alice, let's flip it. Let's say Alice pays Ron. Because let's say that you're actually Ron and you want that money. So you try to go back in here and you try to edit this. What'll happen is, now that you've changed even one character, now what happens is when you try to hash this with this nonce, you don't get a valid block anymore. You don't get 4 zeros anymore. You get something completely different. And then since this hash is now different, this one that's ahead of it won't point to the correct block anymore, and this one will also cascade fail too, and the next one, and the next one, and the next one. So what ends up happening is that you literally cannot alter anything in here without the entire chain breaking. So what you'd have to do is mine it again, do the work all over again, which can take a long, long time, because in the mining network, we're not talking about like 80,000 numbers. We're talking about millions or trillions, actually way more than millions, trillions upon trillions upon trillions at this point, basically. It's just unimaginable how fast it goes. So anyways, so when you mine, you have to do all of that work again. So that's why Bitcoin's, it's called a consensus algorithm. So this whole method is called proof of work, or POW for short. And so that's where you have this nonce and you're cycling it. So that's basically what's going on, is you have to do all this work again, and that costs time, computing power, and energy. So let's say everyone else, all the other block producers, all the other nodes on the network, because there isn't just you, there's actually thousands, maybe tens of thousands of people or operators all operating basically the same software, and they're all using it in a decentralized way. So the way the software works is it will only follow the longest chain. So for you to make this fraudulent attack, you have to first put it in place, and then you have to catch up to all the other people. But if they have more hash power than you, you're not going to win that race. Let's think of it like this. If you're running a marathon and, there's like this long race, you couldn't go back to, let's say you're 60% of the way through the race, and then you decide, oh, I want to change the way I place that water bottle at the first water station, like 20% of the way through. So you run all the way back, you change the water bottle, and then now, guess what? You have to catch up if you're going to win that race. Well, unless you're like, the Flash, you're not going to win it. It's just going to be gone. So you won't be able to catch up. And then when you can't catch up, it means you can't actually have your fraudulent submission actually work. So what magic property that this inherits is that basically anything written into this area here inherits this trait called immutability, meaning it can't be changed. It's like it's written in stone. It would be so hard to change it that it's nearly impossible, just because of the way this whole system works and operates. So what that means, like what the real value proposition of a blockchain does, is that it creates a space it's created this environment where you can trust what is written down will stay written down exactly that same way all the time. So that is really the power. And why that matters so much is that everything that we're building on top of it, like NFTs, all these new things, they're all utilizing this one immutability property as the thing that they're building on. It's like if you're looking at a skyscraper, well, you know that every every window, every piece of glass, all the chairs and things inside that office tower, they're all being held up by the solid concrete foundation below, right? So if you don't have that concrete foundation, if you just like erased it, then suddenly that building would have nothing to stand upon and it would just fall down. And so that is the real foundation right here, is this data space. So we have an array that can contain data that is immutable. Basically, it cannot be changed. And we also have a decentralized network. That means a whole bunch of people who all have copies of the same data. So it's not just like one person has access to this. It's like, no, there's 10,000 copies and they all have to basically agree. So if one person or two people or five people decide to go against the wave, it's not going to hold up. It's very, very hard to attack it, nearly impossible. And that's why, trillions of value have been created onto this blockchain and it still hasn't been hacked, even though, if anyone could hack it, they would, because it's worth so much money. But it's just not possible in today's technology. So basically, we've created immutability in the data space. So this is a huge deal. Why? Okay, so what's the big deal? Basically, what blockchains are doing is that they are trust machines. They automate trust. So just think about that. Is trust valuable? I would say so. Think of anything, right? Like, why would you go to a pharmacy and pay $100 for some medicine when there's some dude maybe in an alleyway that's selling it for $1? I think that's kind of obvious. Why? Because we trust that the person at the pharmacy is going to be selling us the right thing. It's not going to be something that's going to hurt us. So because of trust, we're willing to pay more. What about, police, hospitals, doctors, lawyers, pretty much everything that we rely on, like even when you buy a house, well, you trust that when you pay all that money for the house, that it's going to be yours. What if we lived in a society where you couldn't trust that it would be your house afterwards, right? Then it would be really hard to make that work. If you can't have trust, you can't have a lot of easily flowing activities happening. It's kind of like in a zombie apocalypse when you don't know who you can trust, so you just don't trust anyone and everyone kind of fends for themselves. So trust is one of the major pillars that our entire society is built upon. And without trust, a lot of things crumble. So I would say, yes, trust is extremely, extremely, extremely important and valuable. Okay, so if we can automate that, instead of having to have people, we can actually just free up a whole bunch of productivity. We don't have to be having a whole bunch of people spending their entire waking lives giving the service of trust. So if that's hard to imagine, it's like, okay, well, a bank teller, they work for an agency that basically has trust, right? Like you trust the bank because the bank has a bank charter that's given by the government. And so the government is saying you can trust the bank because we will do something against the bank if they do anything wrong. So okay, I'll trust the bank. So, but to keep that in place, they need to have agencies and government workers that are going to monitor the bank. And so those people basically, they go home, they drive their car, they burn energy, they eat food, they have to live, they need a house to stay in. So all of those things are going into just keeping that service alive. But that's only one step, and that's only one employee. There's all the employees that need to be basically providing that trust. And then down the next chain to the bank. Well, then the bank at the top, the managers, they have to instill trust that their branch is going to work. So again, that they are also living and breathing and using all these resources to keep this thing going. And same thing, tellers, and all the way down the chain. So to provide that service, you're basically using, potentially thousands of people's lives we're supporting to maintain this service, it makes sense when we don't have something else that can do it better. But when we have a machine that can do this for a fraction of a fraction of a fraction of the cost of energy, then yes, it actually starts to make sense. So anyways, so that is, what do blockchains sell? What is their product? Okay, so blockchains basically sell trust as block space. So the block space is that array we are talking about. So that's their product. They sell for whoever's willing to pay for it space to be included in a trusted environment where they can write down a transaction and trust that it's going to stay that way. It's going to be immutable. So basically blockchain's revenue is that the fees that people are willing to pay for that block space. So that's basically, that's about as simple as it gets. It's basically blockchains automate trust. They're trust machines. They're very, very, very good at that. They have other problems that we won't go into now because that's a totally, this was 2008, 2009 when this is all starting. So we're here, more than a decade later. And so things have changed, things have evolved, but that's another topic. But really, it's like when we're talking about NFTs and we're talking about all these things that we're doing with crypto now, it's all built upon the same thing. And so why this is important is because if you ever get sold something that's not included in block space, that doesn't actually have that immutability, or that's posted on a blockchain that doesn't have as much security, then you run the risk of basically not actually getting this benefit. And you're just being sold snake oil, or basically a scam. The real legit thing is when the block space is safe and trusted and secure. So larger blockchains are much, much more secure from attack, like Bitcoin and Ethereum would probably be the two most secure blockchains in the world. But there's other ones as well that, go down. It's like a gradient scale. And also the way that they're set up too. So that's another topic for another day. But basically, the way what Bitcoin does and what it started out doing is it created this totally new thing. It's automating trust, and that is a huge deal. So yeah. So just to sum up here, Bitcoin introduced the invention of the blockchain, but this was only the beginning of what came next. However, this decentralized, immutable, automated trust layer is the foundation that all future value in crypto is actually built upon. So that is why NFTs are different than just trading a JPEG, because they live inside this decentralized, immutable layer. And so because of that, we can prove with certainty who owns what, or at least what address owns what. And that is amazing. That is huge. And that is going to change so much. This is just the beginning. Trading JPEGs is one thing. What about movie rights ownership? That could be tracked. What about who owns a house? That can be tracked. What about who owns this car? So when you have these layers and you have these things, you can actually build apps that are built upon the blockchain using programming. So these are called smart contracts, and you've probably heard of them before. And so that's how we're able to do so much more. So much more. We'll be able to really increase our efficiency in how things are made and things like that. But yeah, I could probably ramble for longer, so I'm going to stop there. And I really hope that you found this helpful and, that you enjoyed this. So thanks so much for listening. Please give it a share to anyone who you think might actually get value out of this. And thanks a lot. I hope you have a great day.